Okay, it's 8:30, so let's go ahead and get started today. Good morning, everybody. How's everybody doing today? So we're a little short-handed right now, but I guess more people will join in a little bit. Okay. To start today, I want to discuss just the last part of the homework, problem 4C, just because I was talking to some people in office hours yesterday, and it kind of highlighted an inconsistency. So I'm going to show you basically how I want you guys to solve the problem, but also explain kind of why it's kind of paradoxical and kind of why you get a different answer basically no matter if you try to approach the problem in several different ways, you'll get a different answer. And the reason is because it kind of violates conservation of mass. But we'll go over that in a minute. Okay? But after that, the plan for today is we're going to finish up our lecture notes on control volume analysis. So we started a little bit of conservation of energy last time, so we're going to finish that up today. We're going to do lots of examples and kind of connect it with the Bernoulli equation, which we covered, a few weeks ago. Right? So besides that, are there any questions that I can answer about the homework before we get started? Yeah, I know one other thing that's happening is that I think I might have rounded a little bit poorly in the solutions for the homework. So if you're getting solutions that are pretty close, I think the big one is 3C with the pillars. So I think some people are getting like 5,000. You're off by about 100 newtons or something like that. That's totally fine. So as long as your process is correct and you're getting something that's really close to my answer, that's what matters the most to me. So I haven't had a chance to really check it yet, but I've looked at people's works that have done it. And it all looks right to me. So don't worry if your answer is just a little bit off, or 5% off of the solution. That's totally fine. Okay. Okay. So let's go over problem 4C on the homework. Okay. Okay. So 4C, we're looking at a situation where we have a swimming fish. So I gave you kind of the example of Dory from Finding Nemo. Okay. So here's your fish. Okay. As best that I can draw it. Okay. And then in 4C, what I tell you is that, say that Dory here is being chased by a shark. So she needs to really, get her fins moving if she doesn't want to get eaten, right? So I think what I said was that in order to escape, or to at least to start to escape, Dory has to accelerate or provide a thrust for herself of 3.5 newtons. And of course, since the fish is moving, we have a moving control volume property. So I gave you V Dory in the problem as 0.35. And so what I wanted you to do is that, or what I told you is that in order to produce this thrust, basically what needs to happen is that she needs to increase the speed of the outlet jet, right? And so with this situation, how Dory is basically producing her thrust is that she's kind of, shaking her tail fin in order to produce like an outward jet of fluid to kind of propel her forward. Okay? So I think in part B, you solve for the situation where, she's just kind of cruising along. What kinds of velocities is that going to be? Okay? But in part C, this velocity has to increase because we're providing a thrust of 3.5 newtons. Okay. Okay. And so let me show you basically the way that I think is the best way, which is different than what I have on the solutions. But I think after talking to some people yesterday, I think this is probably the best way to solve it, at least with the least amount of errors and imaginary numbers. Okay. Okay. And so because we have a force here, we know that we have to apply conservation of momentum. Because out of all of our RTT conservation laws, the only one with a force is linear momentum. Okay. Okay. And so with conservation of linear momentum, I'm going to skip the unsteady term because all the time when we do conservation momentum, we have an unsteady term there. But but we assume that it's steady just so to simplify the math a little bit. Okay, and so what we have, kind of the first form of this, is that we can say that the sum of the forces is equal to integral of u rho w dot n dA. Okay? And notice that, for this case, I switched the u in this case to w, where w here is our relative velocity. And so remember, whenever we have moving control volume problems, we have to switch the carrying velocity to a relative one, because we have to account for how much the fluid is actually crossing into our control volume border. Okay. 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 And so if you look into the lecture notes, what we derived was actually a second form for this conservation momentum equation, if we can assume that it's steady. Okay. So that second form is given by this. And so the second form basically, we just replace this u with another w. Okay? So instead of having u times w, we have w times w. Okay? And so originally, when I solved the solutions for this problem, I actually used this form right here. Okay. But what I used actually was a minus of the force. Okay. And so what I set this equal to was 3.5 newtons. And then I plugged in for W, and then off I went, and I solved for the velocity. Okay, but it turns out I made a mistake in my work, because since our outlet jet is going to the left right here, right? What this needs to be is actually a negative 3.5 newtons, right? Because we have to accelerate the flow going to the left, and if we're accelerating the flow going to the left, then it has to be a negative. Okay? But then if you actually solve the problem like this, you actually get an imaginary number, which is not good. Okay. And so the best way I think to solve this problem is actually to use this form up here. Okay. And so you set this equal to minus 3.5 newtons, and then you solve this as before. And so the only caveat here is that this W right here, this W represents the relative velocity of the fluid crossing the control volume border. So you actually solve for this in part B. Okay. And so all you have to do is just plug in for that value for W from part B, and then you can solve for the only unknown in this equation, which is this U right here. Okay. And so I think that's probably the best way to solve this problem, is you kind of assume that you know W, and then you solve for U. All right. So that's I think the best way to solve that problem. But let me tell you why that this is this kind of breaks things. Okay. And so we know that when we increase U out here, right? So increase kind of the speed of the outlet jet, then Dory is going to have a thrust of 3.5 newtons. Okay. But if we increase the speed of the outlet jet, then what we're doing is we're kind of violating conservation of mass, because we're not increasing the amount of inflow that's coming into the model. Okay. Because if you remember from the problem statement, the fluid in front of Dory is actually still, right? So we say that UN is equal to 0. And so in order to satisfy this condition where we increase the outlet jet, in order to actually satisfy conservation of mass, then Dory has to actually swim faster, which is actually what we want, right? But in this particular problem, I basically assumed that V Dory was the same. Okay? And so this kind of the fact that we're increasing the outlet jet for a moving control volume without increasing the speed of the control volume, it kind of, at least for a brief instant, it violates conservation of mass. Okay, so it's a very kind of paradoxical answer. Okay, but the reason that this can be is that we're only considering the very brief moment right when she starts to accelerate. So it's at the very brief moment. So right when she produces thrust, basically immediately after we solve this problem, her speed is going to increase, which is what we want. And so we're solving this problem at the very brief instant, right when she makes that first shake of her tail fin in order to start accelerating. So for that brief moment, you kind of violate conservation of mass a little bit, but it's only just for a very brief moment. So if you're struggling with force C, this is kind of the thinking, and this is kind of the way that I think is kind of the best way to solve this problem. Okay. All right, any questions on this? So if you're having trouble with 4C, definitely give this method a try. And then if you have any more questions on it, definitely you can contact me, through email or Discord or whatever. Okay, so let's get back into conservation of energy. Okay. So conservation of energy is our last kind of conservation law that we're going to apply RTT to. Okay. And so to this point, we've got conservation of mass, conservation of linear momentum, conservation of angular momentum, and now conservation of energy. Okay. And so conservation of energy kind of has the most going on, but it's also really important for a lot of devices. Okay. And so last time what we did was we, anytime we apply RTT, we have to define what our B variables are, right? And so that we say that big B is equal to the total energy. Okay. And so that's going to be our mass times internal energy plus mass times velocity squared over 2. And so this is our kinetic energy, okay, plus mass times G times Z. Okay. And so that's our potential energy. Okay. So our energy here has 3 different terms that we need to consider. Okay. So that's our big B. And then our little b here is just everything here divided by n. So we have this internal energy plus kinetic energy plus G, Z. Okay. Okay. And so we're going to plug this into our Reynolds transport theorem. Okay. And so the other thing that we need to specify is that we need to specify the production term. Okay. I think this is what we ended on last time. And so remember, the production term represents, from the perspective of a control volume, how can energy kind of appear in the system. Okay. And so we said that there's kind of 2 contributions to this. Right, so we said that there's one term called Q dot, okay? Again, not to be confused with regular Q, which is our flow rate. Okay. And so remember this Q dot right here, this is heat transfer. Okay. Okay. And so one of the primary ways that energy is transferred between objects is through heat, right? And so it's the same with fluids. If you heat up a fluid, you can increase its energy. If you cool a fluid, you take away some of its energy. Okay? And we're not going to get too much into heat transfer here because there's a whole nother class about it. Some of you might have enrolled for it in the next semester. Okay? But it's there, and it's important. And this is and this W.net right here. This is any mechanical work that's done on the system. And so we'll be dealing more with this term on the right here. So these are things like if you have like a pump that's driven by a shaft or a turbine that's going to be turning around, that's what this mechanical work is. So it's kind of like mechanically you're putting work into a fluid or you're taking it out. Okay. And so if we put these together, we can form our conservation of energy expression. And so we just apply RTT. And so first we have our unsteady terms. We have partial T of E rho dV. Okay. And so I'm just to have shorthand, I'm gonna define little b to be little e. Okay. So little e is just gonna be the sum of all of these terms right here for the internal energy, kinetic energy, and gravity. Okay. And then plus integral of E rho U dot N. So we have our carrying velocity, dA. Okay. And these are going to be equal to our production terms. Okay. So we have Q dot net and W dot net. Okay. Okay. So that right there is our RTT expression for conservation of energy. But we're going to work on this a little bit because right now it's not really in that useful of a form that we can actually perform calculations on. And so we're going to work on this first. First of all, we're going to introduce pressure because we don't see pressure in here. As we know from Bernoulli, pressure is an important thing that contributes to the energy. And so we're going to introduce pressure into here, and then we're going to work on the terms a little bit, and then we'll get an expression that we can actually use for calculations. Okay.
Quick question. What's E again?
Little e is this sum that I've boxed up here.
Okay.
So it's the sum of the internal energy, kinetic energy, and the gravity.
Okay.
Potential.
Thank you.
Mhm. All right. One more assumption, just before we move on to the next page, and it has to do with the heat transfer term. So all the heat transfer stuff. Basically, we're saying that I'll leave that for 407 next semester. So we're not going to consider it that much in this class. And so most of the time, we're going to assume that Q dot net is equal to 0. Okay? And so we're going to assume that there's no heat transfer into or out of the system. And if you've taken thermodynamics or you're taking it right now, you might be familiar with the term adiabatic. So all adiabatic means is that we have no heat transfer coming into our system. So we're looking at just purely just mechanical, physical forms of work and energy. Okay. Any questions on this? Okay. Okay. And so now let's let's talk about pressure, because pressure, if we think back to Bernoulli, pressure was one of the important terms in our Bernoulli equation. Okay? And so it's a little bit weird that we're talking about energy right now and pressure is not present, right? It's like he was kind of left off the invitation to the party, right? So let's talk about that. So even though pressure is not really a form of it's not a pure form of energy just by itself, right? And so when we formed our equation here for big B and little b, we didn't put pressure in there because pressure is not really a form of energy. Right? But pressure does have an effect on fluids, right? And the way that pressure has an effect on the energy of the fluid is that pressure can perform work on a fluid. Right? Because what is pressure? Because pressure is nothing more than just a force divided by an area, right? And so just like any force that acts on an object that causes it to move, can generate work on it, right? So just like, if you have your computer mouse, you take your hand and you push it with the force across your desk, right? Your hand is performing work on the computer mouse. So pressure is just like a force that can perform work. Okay. And so just to kind of illustrate this, let's draw just a simple pipe flow, just to kind of see. Okay? And let's say that we have flow in this direction. Okay? And say that at the inlet here, we have a P1, and at the outlet here, we have P2. Okay? And so since pressure is nothing more than just a force over area, right? Both of these pressure forces both of these pressures are exerting force on the fluid. Okay? And so what we can do, based on the situation, is that we can come up with a mathematical expression for the work done by a pressure force. Okay. And so that's given by the following. So we have work dot press is equal to integral of minus P. Okay. Remember, when I do P with the ponytail, that means pressure. So don't get confused with the density. dA. Okay. Okay. And so this is basically the pressure force here. So we basically have pressure times area, which is going to produce a force, and then we multiply that by the carrying velocity, which will produce work. Okay. Okay. And so you might be asking, what's up with the sign convention here? So why do we do negative? Okay. And so the reason we do negative is that typically, since the flow is going from left to right, we say that the pressure force is doing positive work on the inlet. Okay, or at least that's what we want to say. And since we know that the carrying velocity is negative at the inlets, in order to kind of cancel out that negative, we have to add an additional negative over here. So it's just kind of a sign convention thing. And just to kind of be consistent with, you know, our definition of work, we put positive work that causes motion in that direction. So this negative here is kind of to cancel out the sign convention from the carrying velocity. Okay. Okay. Any questions on this? Okay. And so what we can do now is we can take this W dot pressure and then we can add this to our expression, because this is just a form of the mechanical work, right? Because if we go back to our expression here for the conservation of energy, we have this W dot net term. Okay? So that W dot net can be any kinds of mechanical work. And so we can say that one part of W dot net will be the pressure force. Okay. Okay. And so the other type of work that we're going to consider for fluids is called shaft work. And so for calculation purposes, we're going to consider shaft work to be every other type of work that you can do in a fluid. But I'll tell you just briefly, you know, why it gets this name. Okay. And so this type of work gets its name is because, you know, typically when you have a pump for a system, you know, it might go something like this, right? And so, you know, the way some pumps work is that you have kind of a spherical or like a device that looks like this, or cylindrical device. And the way that we input energy into the fluid is that we have this fan with fins in the middle, and then we have a motor on the outside that kind of twists this fan. Okay. Or not twist, it rotates the fan. Yeah. Okay. And so by rotating the fan, we're literally pushing the fluid through, you know, and kind of adding mechanical work to the fluid. Okay? And so this shaft work represents basically the amount of work that you do on this shaft to make the fan rotate. Okay? Okay? And so that's kind of where it gets its name. But you know, we're going to use this term shaft work to denote kind of everything else, all the other types of energy that we can add to the. Okay. And so if we add the pressure term into our conservation of energy, and then we consider the rest of the W dot net to be shaft work, then we get this following expression, which is probably the most useful form for calculations. Okay. And so this is kind of the final form for RTT, for conservation of energy. Okay. And so we have partial T of E rho dV. Okay. Okay. And so that's our unsteady term. So that's the same as before. And so now we have our inflow outflow term. And so I'm going to expand this now so that it contains basically everything. Okay. And this is rho U dot N dA. Okay. And so that's our inflow outflow term. So you can see I've expanded all the different types of energy and work that we can put in. In particular, I've added the pressure term to this because, you know, that's kind of the pressure force that's being acted on the fluid. Okay? And all this is equal to W dot shaft. Okay? And so this is the form of RTT that we're going to use for the next 2 or 3 examples, you know, that we'll use for calculation. So this form is a lot more convenient because, first of all, you know, most of the times we're going to assume that the flow is steady. And so we can cross out the first term there with the time derivative. But also, you know, we've broken up our inflow outflow term into things that we can actually compute, like the pressure and the velocity and the height differences. Okay. And so, you'll probably notice something about this expression. And in particular, it's these guys. Okay. And so these guys should look very familiar to you because these are our Bernoulli terms. Okay. And that's no coincidence. And so that's, we're going to come back to that a little bit later because we're going to draw the connections between this conservation of energy expression and our Bernoulli equation and see how they relate. Okay, so the next thing we're going to do is an example. But before we go into that, are there any questions on this?
Yeah, for the energy inside, is that pressure divided by pressure or pressure divided by rho?
Yeah, that's a good question. So that's pressure divided by density. So it's pressure divided by rho.
Okay.
Yeah. Mm-hmm. Okay. So let's do an example. Okay. So in this example here, let's consider a pump. Okay. Okay. And so a pump, we're going to use the term pump quite a lot in this class. And pumps come in all different shapes and sizes. You have anything from your bike pump to like an industrial size pump. Okay. And so pump is just another word for a device that can drive flow. Okay. Okay. Or in other words, what a pump is going to do is we're going to input energy into the flow, and then that's going to either speed it up or increase its pressure. Okay. Okay. Or one other thing I should mention too, or is that we can use a pump to basically drive a flow up to a certain height. And so if you live on kind of on one of the upper floors of your apartment, there has to be a pump there that basically gets water from the ground up to your third or fourth floor apartment. Okay. Okay. And so let me draw just kind of a schematic here. Okay. And so this kind of matches the figure that we had before. So I'll draw it a little bit nicer. Okay. And so we can say that the flow is coming in here, right? So let's put some numbers on this. So we can say that we know that the flow rate in is going to be equal to 0.02 meters cubed per second. Okay. We know the diameter at the inlet. So the diameter at the inlet is going to be 6 centimeters. Okay. We know the pressure at the inlet. And so the pressure at the inlet is going to be 125 kilopascals. Okay. And then we know the outlet conditions too. So we know that the diameter of the outlet is going to be 2 centimeters. Okay. And the pressure at the outlet is going to go up, is going to be 450 kPa. Okay. And so what we want to solve for here is, in order to produce these conditions, so we can see that as the flow goes through this pump, the pressure rises from 125 kilopascals to 450. Okay? And so what we want to solve for is what is the power that we're going to put in. Okay? And so in particular, if we connect this back to our RTT expression, we're going to solve for W dot shift. Okay. Okay. And so just like every control volume problem, we're going to start with actually drawing our control volume. Okay. So in this case, it's a pretty straightforward system. We have one inlet and one outlet. So we just have to make sure that our control volume kind of encompasses that and encompasses the main part of the pump itself. Okay, so in this case, this is an adequate control volume for this problem where it encompasses the pump. Okay. Okay. All right. Any questions on the problem setup? Okay. Okay. And so eventually we're gonna apply conservation of energy here, right? But in order to apply conservation of energy, we need to solve for all of the quantities in this expression. Okay. And so we need to solve for the pressure, we need to solve for the velocity, and we need to solve for the height and the internal energy. Okay. Right. And we're going to assume that it's steady, so we're going to get rid of that guy. Okay. So let's start solving this. All right. So first let's do some assumptions. Okay. And so most of the time, unless it's given to you in the problem, you can assume that the internal energy does not change between inlet and outlet. Okay. And so if the internal energy does not change, then that term, that EINT that we have at the beginning of here, we can assume that that there's going to be no change, so we can cancel out that term. Okay. And so remember, internal energy is kind of a way to express kind of the temperature of the fluid. So unless it actually tells you that the temperature is changing, then you can assume the internal energy is zero. And most of the time, if you don't have any heat transfer, you can say that changes in internal energy are going to be pretty negligible most of the time. Okay. And so the other thing that we'll assume, which is kind of given by the figure here, is that there's going to be no height change in between the inlet and outlet as well. Okay. And so the potential energy term that we're going to have in our RTT is going to be also, no change. So we're not going to consider that. And so the only terms that we're going to consider are basically just the pressure and the velocity. And so we're not given velocity here, but what we are given is the flow rate. Okay, so we're given Q in, and so what we can do is we can use that Q in and solve for the velocities. Okay, so let's go ahead and do that. And so just like we do in most problems, we're going to start with conservation of mass. Okay, because conservation of mass is really great at helping us find velocities. Okay? And so in conservation of mass, we have partial t integral of rho dv, okay, plus m dot out minus m dot in. Okay, all that's equal to 0. We say this is 0 because of steadiness. Okay, and so we get that m dot out is equal to m dot in. Okay, as is usually the case for a steady flow like this. Okay, and so if we substitute this, we say that m dot out is equal to rho a out u out, which is rho a in u in. Okay, and so cross out the rows here, and we say that q out is equal to q in. Okay, and so the flow rate in and out of our system has to be the same because we have conservation of mass. Okay, and so let's actually use this to solve for the velocity. So since we know that q in is equal to 0.02 meters cubed per second, okay, this has to be equal to a in u in. Okay, and so we can say that u in is equal to 0.02 meters cubed per second divided by a in. Okay, right, we can compute A in from the diameter, right? So we're given a diameter of 6 centimeters for our inlet. And so if we plug that in and we compute its area, pi over 4 d squared, we plug in the numbers, what we get is 7.07 meters per second. Okay. And then by conservation of mass, Q in has to equal to Q out. So we can say that Q out has to equal 0.02 meters cubed per second, which is equal to A out, U out. Okay. We can say that U out is equal to 0.02 meters cubed per second divided by A out. Okay. And so you perform the calculation. So what you get is 63.66 meters per second. Okay. All right. Well, it's kind of lagging a little bit. Okay. Any questions on this? I think the stream is still, I think Zoom is still catching up a little bit. Okay. Sorry about that, everybody. Is everyone still with me?
Yeah.
Okay, I disconnected for a second, so my Zoom closed and it rejoined. So is everyone still seeing the conservation of mass here on the screen?
Yeah.
Okay. Okay. Yeah. Sorry about that. I think my internet just kind of crapped out for a second. But are there any questions about how we applied this conservation of mass right here? Okay. And so now that we have the velocities at the inlet and the outlet, oh, okay. I think I stopped screen sharing. Come on, Spectrum.
Yeah, Spectrum's been fluctuating for me as well lately.
Yeah. Okay, here we go. Go back, share content, screen. Okay. And we're back. Okay. Okay. And so now that we have the velocity at the inlet and the outlet, we can apply conservation of energy, okay? Because we'll have all the terms that we need. Okay. So let's go ahead and do that. Okay. And so let me write out the full expression here, and then we'll cross out the terms from our assumptions. So we have partial t integral of E rho dv, okay, plus integral of E internal plus P over rho plus U squared over 2 plus GZ, okay, rho U dot N dA, and all this is equal to W dot shaft. Okay. Okay, so let's start crossing out some terms according to our assumptions. Okay, and so first of all, you know, we have a steady situation, so we can cross out this guy. Okay. Next, we assume that there's no change in internal energy, so we can cross out that. And we also assume that there's no change in height, and so we can cross out that term right there too. Okay. And so after we, you know, perform these integrations and we do this, we get the following. We get P out divided by rho, okay, plus U out squared divided by 2, okay, is equal to rho U out A out, okay, minus the same things at the inlet, okay, and so the inlet will have P in divided by rho plus U in squared divided by 2, okay, rho U in A in, okay, And all this is equal to W dot shaft. Okay. And so we have everything here that we can plug in. But before we do that, I want to just kind of talk about each of these first two terms. Okay. Right. And so remember that RTT talks about the transport of certain kinds of properties into and out of our control volume. Okay. And so this first quantity right here, you can kind of interpret it as the total energy flux out of our domain. Okay. And then this this term right here, this is the total energy flux into the domain. Okay. And so if we plug in all the numbers, what we get is W dot shaft is equal to 46.53 kilowatts. Okay. Right. Because from the problem we had P out and P in, and now that we have a U out and U in, you know, and of course we have the density, we have the velocities, and we have the areas. Okay. We can just plug in everything into this expression to figure out, you know, how much power that we're putting in. So, you know, in order to operate this pump under these conditions, our motor or whatever has to input a power of 46.53 kilowatts. Okay. Okay. Any questions on this? Right. So the question is, why is GZ 0 again? So GZ itself is not 0, but Z in is equal to Z out. And so once we perform the difference in between them, then they equal to 0. So, you know, in cases where you don't have any height change, you can cancel out that term. Okay. So that's basically a simple pump example. Okay. So kind of a way that you can see that when you input energy into a system through a pump, you know, you can increase its velocity and you can increase its pressure. Okay. Okay, so let's now do an example of the opposite. So let's look at a turbine. Okay. And so a turbine is another common form of fluid mechanical devices. Okay. But they're kind of the opposite of a pump. So, you know, for a pump, you know, we input mechanical energy in order to increase the energy of the fluid. A turbine does the opposite. So it takes a flowing fluid and it extracts energy. Okay. Okay. And so that energy that it extracts, it can be used to do other useful work. Okay. And so I think the one that's probably most common today is that you can use a turbine to produce electricity. Okay. Okay. And so you can imagine putting like a turn wheel into a river. So the river itself is turning the turn wheel, and that turn wheel itself is like a turbine because it's taking energy from the flowing fluid and turning it into mechanical energy, right? Another example is like a windmill. And so a windmill basically takes energy from a flowing wind and turns it into, you know, either mechanical work. And, you know, if you've ever driven to Palm Springs, you've probably seen, you know, all those huge wind farms with, like, you know, the wind turbines out there. So they have all these windmills out in the wind where the wind turns those windmills and it turns into electricity for the surrounding areas. Okay. Okay, so let's look at kind of a very simple form for a turbine. Okay. In particular, for this example, we're going to look at a steam turbine generator. Okay. And so it looks like this. Okay. And so let's define the conditions at the inlet. So at the inlet, we have an inlet area of 0.01 meters square. Our velocity at the inlet is going to be 30 meters per second. Our pressure at the inlet is going to be 60 kilopascals. Okay. And in this case, we do have an internal energy at the inlet. Okay, we can say that E int, or we can say that big E, I should say. Big E1 is going to be equal to 3350, and the units for this is kilojoules per kilogram. Okay. And so those are the conditions at the inlet. Okay. And at the outlet, we have the following conditions. Okay. So we have A2 is equal to 0.02 meters squared. Okay. I know I didn't draw this to scale, but I'm paid to be an engineer, not an artist. Okay. Okay. Our velocity at the outlet is going to be 20 meters per second. Our pressure is going to be 500 kPa. Okay. And our energy, internal energy at the outlet is going to be 2,500 kilojoules per kilogram. Okay. So if we assume that our density is waters, we can say that our density is kilograms per meter cubed. Okay. What we want to solve for in this case is how much energy or how much power is being generated by this turbine. Okay. And so again, we're going to apply our conservation of energy with Reynolds transport in order to solve for this. Okay. Okay. And so in addition to this, we're going to assume that, you know, we're under steady conditions. We're going to assume adiabatic, and we're going to assume that there's no height change in between the inlet and the outlet. Okay. And so those are our assumptions. Okay. And then just like we always do, we're going to draw our control volume with the dotted lines, just like. Okay. All right. Any questions on the problem setup? Okay. All right, so for this problem, it's a little bit more straightforward because we're basically given all the information that we need. So we can just basically straight up apply RTT for conservation of energy. Okay. And so let's go ahead and start plugging it. Let's go ahead and write out the expression. Okay. Say partial T rho E dV, okay, plus integral of E internal plus pressure over density plus U squared over 2 plus GZ, okay, times U dot N dA. Okay, there's a density here too. And this is equal to W dot shaft. Okay. And so let's apply our assumptions on this guy. Okay. So first of all, we're going to cross out the unsteady term. Okay. And the fact that we have no height change, you know, we can cross out this guy too. Okay. And so we just, you know, we just apply the formula now. So then we evaluate this at our outlet and our inlet. And so we're going to have E out plus P out divided by rho plus U out squared over 2 times rho U out A out minus same quantities at the inlet. So we have U E in plus P in divided by rho plus U in squared divided by 2. Okay. Rho U in A in. Okay. And all this is equal to W dot shaft. Okay. Okay. And so all I did was I just evaluated that integral, at the inlet and the outlet. And so since we're given all these terms, we can just kind of just plug them all just straight in. Okay. Okay. And so we plug in all those quantities. What we get is minus 5.035 times 10 to the third kilowatts. Okay. Okay. And so you can see here that our answer here is negative, right? And so that's not by coincidence. So the fact that our answer here is negative means that energy is being extracted from the flow, right? So the fluid here is losing energy, and that energy is turning into shaft work, which we can use to produce electricity. Okay. And so whenever you have a turbine, the work dot shaft that you produce or that comes out of it should be negative because the fluid is losing energy to the shaft. Okay. All right. Any questions on this?
Can you explain why you're multiplying that whole the E out plus P out to the rho U out A out on the right hand side?
Sure. Yeah, definitely. So this quantity right here, rho A out, rho U out A out, comes from these integral expressions. So this density right here comes from this density right here. This velocity right here comes from the carrying velocity, and then this area right here comes from this dA right here. So it's basically just a result of performing that integration, assuming that all of these quantities are kind of constant, and we can just perform the integration for A.
Okay, thank you.
Yep. Mm-hmm. Okay, so the question is, what is negative? So the W dot shaft that we get out right here is negative, right? And so the reason it's negative is because this is a turbine, and so the fluid is losing energy to the turbine. So that's why it's negative. Yeah.
All energy from turbine is negative because it's being lost?
Yes, exactly. Yeah. Yeah, so for a pump, we have positive energy because the fluid is gaining energy in between the inlet and the outlet. And for a turbine, the work shaft is negative because the fluid is losing energy. So that's kind of one good sanity check that you can do. So most problems, unless I ask you to determine if it's a pump or a turbine, most problems will say, this is a pump or this is a turbine. And so you can use that information to kind of check your work at the end. All right, so the question is it always out minus 10? Yes, it is, because remember the sign convention for our carrying velocity right here. And so the positive and the negative comes from the fact that for the outlets, we have a positive carrying velocity, and for the inlets, we have a negative carrying velocity. So this sign convention, the fact that we have a positive outlet and a negative inlet, comes from this U dot out term. Yeah. U dot N. So the question is, what is the subscript for the first internal energy? It's just out. It's just my iPad is acting up. Yeah. So it's just the internal energy at the outlet. It's hard to write small in this thing because it's a piece of crap iPad. Mm-hmm. Yep. Okay. So those are two kind of examples. We did one with the pump and one with the turbine. So I do have one more example planned today. But I do want to kind of take a little bit of a detour and then compare what we've just looked at to Bernoulli equation. Okay. And so I'm going to write our RTT for conservation of energy, but I'm going to basically apply it for a single inlet, single outlet, and also I'm going to assume steady. Okay. So for steady, single inlet, single outlet, which is the two examples that we just did. our conservation of energy for RTT looks like this. Okay? And so we have E out plus P out over rho, okay, plus U out squared over 2 plus GZ out, okay, times rho U out A out, okay, minus the same quantities at the inlet. Okay. So we have E in plus P in divided by rho plus U in squared divided by 2 plus GZ in, okay, rho U in A in, okay. And then I'm going to set this equal to Q dot net for now, okay. And so I'm going to bring back the heat transfer term just temporarily. So this is just this is just so that we can compare with Bernoulli. Okay? And then for now, I'm also just going to ignore any shaft work. So this is, you know, just passive flow. So we're not going to be inputting any energy or just extracting. Okay. 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 All right, so the next thing I want you guys to look at are the terms that I've circled there. So the term that I've circled first is m dot out. Okay, so that's just the mass flow rate out, and in the other one we have m dot in. Okay, and so remember our assumptions here. So we assume that we are looking with a single inlet, single outlet, and the fact that it's steady means that we can basically say that m dot out is equal to m dot in. Okay? And so I'm just going to drop the subscript for that, and I'm just going to say that this is just going to be equal to m dot. Okay. Okay. All right. So since we have a single m dot for this entire system, I'm going to divide this entire system by m dot. Okay. And at the same time, I'm going to rearrange some of the terms. Okay. Okay. And so if we divide the entire system by m dot, you know, we basically just have the terms in parentheses on the left-hand side. And on the right-hand side, we have a q dot net over m dot, which I'm going to define in a second. First, let me write out all the other terms. Okay. In particular, I'm going to write them in terms of differences in between each of the different types of energy and work. Okay. And so first, we have the difference in internal energy. Okay. So we have E out minus E in. Okay. Plus P out over rho minus P in over rho. Okay, so that's the difference in the pressure terms. And then we have our difference in our kinetic energy terms. We have U out squared over 2 minus U in squared over 2. Okay, plus G Z out minus Z in. Okay. And so this is equal to Q dot net over M dot. Okay. And we'll say that this is equal to little q dot. Okay. And so what this little q dot basically says is that this is the heat transfer per mass. Okay. And so the units for that q dot are going to be kilojoules per kilogram. Okay. But that's a little bit less important in this context. Okay. So it's a lot. So I think I'll give everyone just a minute just to kind of write it down. Okay. And so, you know, I put this equation in this form kind of very purposefully. So what I have here circled in green, you know, you should recognize this from week 4 or 5, whenever we did Bernoulli, right? Because what I have circled in green right here, this is our Bernoulli equation. Okay? Right? And so through the conservation of energy, you know, with some assumptions here, basically what we got from our conservation of energy is our Bernoulli equation, okay? Plus some extra stuff, and that extra stuff will be actually pretty important, okay? And so let me actually write down the units for this guy before we turn the page. And so this Q dot has units of kilojoules per kilogram, okay? And so basically energy over mass, okay? It's a little bit of a weird unit, but you know, that's kind of what we get by dividing by m dot. Okay. Any questions on this before I turn the page? Okay. Okay. And so I want you guys to think back to our Bernoulli equation, right? So with our Bernoulli equation, remember we had 4 assumptions that we had to make, right? And so we had to assume that the flow was incompressible. We had to assume the flow was steady. We had to assume the flow was inviscid, so no velocity, so no viscosity. And we had to assume we applied along a stream. Okay. And so up to this point in RTT, you know, obviously we've already assumed that the flow is steady. Okay. And you know, I didn't go over it explicitly, but the fact that we can pull this density out and that it's constant, you know, we've already assumed that it's incompressible as well. Okay. The one assumption that we haven't made yet is that we haven't assumed that there's no viscosity. So we can have viscosity in here. Okay. Okay. And so if we take this expression that we have over here and we kind of just ignore Bernoulli, because remember what I have in green right here, you know, what I have in green right here, this assumes that there's no viscosity, right? Because this is just our Bernoulli equation. And so, you know, the fact that we have viscosity means that everything else right here, this E out minus E in and Q dot, you know, that means that when we do insert viscosity into our expression, these are the terms that come out. Okay? And so blue terms are directly result from viscosity. Okay. And so if we ignore basically everything in the green on the previous page, we're left with the following expression. Okay? We have E dot out minus E dot in, or E out minus E in, sorry. There's no dot. Minus Q dot net, okay, has to be greater than 0. Okay. And this is the you know, effect of viscosity. Okay. Right. And so in other words, what this affects is that you know, if we have viscosity, then we lose some energy from viscosity. Okay? And so it's not often, we will always lose energy from viscosity. Okay. And what this tells us is that, you know, because, you know, viscosity affects, it doesn't affect the pressure, it doesn't affect the velocity, it doesn't affect the gravity, you know, what this affects is the internal energy. So this energy lost will always come in the form of heat. Okay? Okay. And so it's been a while since we've talked about viscosity, but you know, I want to draw kind of one comparison between viscosity and probably another phenomenon that you're probably really familiar with, right? And so just by reading this description here, that you know, viscosity causes energy losses in terms of heat, right? There's another phenomenon that does basically the exact same thing, and that's friction, right? So if you rub your hands together, I mean, my hands are extremely sweaty right now, so it doesn't really work. But if you rub your hands together and they're dry, right, you know that the friction in between your hands will cause your hands to heat up, right? And so the reason that occurs is because that the kinetic energy that your hands are you know, that are moving your hands, that energy is getting dissipated in terms of heat because of friction, okay? And so viscosity is kind of like the friction for fluids, okay? Okay. And so if you have a fluid with the viscosity, you know that there's going to be some energy losses there, and that energy losses are going to occur due to heat. Okay. Okay. All right. And so if we include this effect of the losses, okay, so we call these losses, we can write kind of an improved version of the Bernoulli equation, or what's called the extended Bernoulli, and I'll do that on the next page. Okay. Before I get there, are there any questions on this? Yeah. Yep. Okay. And so the extended Bernoulli is given by the following. Okay. And so our extended Bernoulli starts out with just regular Bernoulli. Okay. So we can have P out over U out, or P out over rho plus U out squared over 2 plus GZ out. Okay. And this equals to the same things at the inlets. We have P in over rho plus U in squared over 2 plus GZ in. Okay. And then to this, we're going to add some additional terms. You know, first of all, for shaft work, you know, we ignored it at first, but we're going to bring it back now. Okay. Minus our losses. Okay. And so our extended Bernoulli basically is our old Bernoulli, but we've added these two terms over here to account for, one, we can account for shaft work if we have a pump or a turbine, and we can account for the losses if we have viscosity. Okay. Okay. And so what this tells us is that, remember, you know, remember our sign conventions for work dot shaft. So if W dot shaft is positive, then we have a pump, right? And so what this tells us is that, you know, if we do have some viscous losses in our system, then we can overcome those losses by inputting power in the form of a pump. Okay? And so, you know, that's kind of another purpose. Sorry about that, everyone. I disconnected again. Okay. And so this kind of shows another purpose of the pump, where a pump, you know, partially it's to add energy to the fluid, but you can also use a pump to overcome any viscous losses. Okay. Okay. Any more questions before we do a super quick example? I might start this example and then I might finish it up next time because we only have 5 more minutes. Okay. And so this example is basically, we're going to see how to use this extended Bernoulli. Okay. So let's consider a fan. Okay. All right. And so let's say that we have a fan that looks like this. Okay. And so this could be anything like a ceiling fan or a fan or just a fan on a stand that you have in your house. Okay. And so the fan is going to drive flow. It's going to go this way. Okay. And so let's draw our control volume around this guy. Okay. And then the outlet of the fan, we have some things here. Okay? So we have D2 is equal to 0.6 meters. Okay? And we saw that P2, we know that P2 is equal to 0. And we also know that U2 is equal to 12 meters per second. Okay. Okay. And then our upstream value for the fan is going to be somewhere, you know, kind of far away from the fan. So we say far away from the fan, our velocity is going to be 0, our pressure is going to be 0, and our A in is going to be very, very large. Okay. Okay. And so what we also know is that W dot shaft is going to be equal to 0.4 kilowatts. Okay. And so given the situation, what we're going to use is we're going to use extended Bernoulli to solve for the losses in this fan. Okay. Okay. And then what we're also going to do is we're going to solve for the efficiency. Okay. And so how efficient is this fan? How efficient is this fan at blowing the air? Okay. And we also know the density of the air. The density of the air is going to be 1.23 kilograms per meter cubed. All right, any questions on this? Okay. All right, so the reason I gave you this example is because it's a very unique situation, okay? And so it's unique in the fact that we have 0 velocity at the inlet, and our inlet area is also very, very large. So in this situation, you know, when we're kind of considering, you know, a very, very large area with no velocity, right? It's actually really hard to apply our RTT. Okay. Okay. Because remember, as part of RTT, we have to multiply by the carrying velocity and the area. Okay. But when the area is not really given to us, and that is really, really large, and our inlet velocity is 0, you know, this makes it really hard to do. Okay. Because the only other time that we saw an inlet velocity of 0 is when our control volume was moving, right? And so if we have an inlet velocity of 0, but we're moving towards the flow, you know, that's fine, because we have a relative velocity in this case. But in this case, we have a stationary control volume and 0 inlet velocity. Okay. And so this makes it really hard to apply RTT because, you know, we can't really quantify things at the inlet. Okay. But what we can do in this case is that we can apply the formula that we just went over just now, which is our extended Bernoulli. Because extended Bernoulli, you know, it doesn't depend on the inlet area or the inlet, well, it depends on the inlet velocity, but then we don't need to multiply by the inlet area. Okay? And so as long as we apply our extended Bernoulli along a streamline, just like we did before, you know, we can use that to compute this problem, and it'll allow us to account for the losses and the shaft work. Okay. Okay, but I think I'll save that for next time because it's 9:45 and I don't want to keep you guys too long. Okay. So thank you guys for tuning in today. I apologize for the technical difficulties. You know, hopefully that doesn't happen too much in the future. And so, you know, since it's the end of the week, I posted a new minute paper for this week for week 8. And so if you can go onto Canvas and just briefly mention what you thought was the most important point this week, what you thought was the muddiest or the most confusing point, and just any feedback for the class, I would really appreciate it. But if not, you know, definitely, you know, have a great weekend. You know, our homework is due this Friday, so if you have any questions on that, definitely, you know, send me a question. and have a good rest of your day. So thank you, everybody, and I'll see you guys next week.
Thanks, Professor. Enjoy your weekend.
Thanks, you too. Page 1, sure. This one or the next page? Oh, page before, okay. Oh, back one page, sorry.